Welcome back everybody, Gary Simmons here with lesson 55 of the Dead Earth game development series, brought to you by the Game Institute. In this lesson we are going to write our generic switch script, which, as we saw in the last lesson, will allow us to complete not only our power generator sequence, but will be a reusable script that we can use in the future to create all types of sequences and puzzles. Before we do that though, we need to write a support class that our generic switch is going to use, and that's the Material Controller class. If I just switch back to the finished version of the Creeper project and select my Power Generators switch trigger, you are reminded that a Material Controller is a class that stores a reference to one of our project materials, along with a group of settings that will be applied to that material when the Material Controller is activated. And that is how material controllers work. We give it a reference to one of our project materials and a group of settings, and then when we call the activate function of the material controller, all of those settings will be applied. And we can also call the activate function passing in false, meaning we wish to deactivate the material controller, which will revert the settings back to what they were when we first pressed play. And that's important because one of the useful features in the editing environment in Unity is that changes that we make to materials do persist play mode. So when we're in the editor and we don't wish those play mode changes to persist when we leave play mode, we need to create a system so that the material controller can revert its properties back. And what you're going to see is that the material controller also has an onStart function. Now the material controller is not a mono behavior, okay? So it's not going to have its start functions called by Unity, but it will almost always be used as a field of a mono behavior. And the mono behavior in its start function should make sure that it calls the start function of all of its material controllers, and this will give each material controller a chance to back up its properties before any alterations are made to the material via a call to its activate function. So in the case of our generic switch trigger, what you're going to see is in the start function of that behavior, it's going to iterate through all of the material controllers in its material controllers list and call each material controller's onStart function. What the onStart function will do is create a backup of the diffuse texture, color, the normal map, the normal strength, the emissive texture, and the emissive color, so that when it needs to revert back, either via a deactivation of the material controller, or if we exit play mode, those settings can be restored. Furthermore, you're going to see that in the start function of a material controller, it's also going to register itself with the game scene manager. The game scene manager needs to store a list of all of the material controllers that are in use, so that when we exit play mode, or in the case of Creeper, when we exit the game scene, and the game scene manager is destroyed, in its onDestroy function, it can iterate through a list of all of the registered material controllers and instruct each one to revert its settings back to their edit mode states. And this will also solve a problem if we have multiple material controllers across multiple game objects referencing the same material. If we had Object A and Object B, and both of them had their own material controllers on them with their own groups of material settings, but they both held a reference to the same material, we wouldn't want a situation where both of them could register themselves with the game scene manager. You could imagine a situation where Object A is activated and applies its changes to the material, but then Object B is started up, its onStart function is called, and it makes a backup of the material, but of course those properties have already changed at that point, so it's not making a backup of the original edit mode properties. So our game scene manager will make sure that if there are multiple material controllers referencing the same material, the first one is the only one that gets stored in the game scene manager's registration list, and will correctly reflect what the properties were of that material before we entered play mode. So going back to our project, I'm going to drill down into the scripts folder, and I'm going to create my material controller in the utility folder. So I'm going to right click and choose to create a new C# script. I'm going to call this Material Controller. I'm then going to open up Material Controller in MonoDevelop. We will delete the start and the update functions. Material Controller will not be a mono behavior, it will be a straightforward C# class. However, we do wish this class to be serializable, so I'm going to add the attribute to this class, system.serializable. By using the system.serializable attribute, we know that if one of our mono behaviors has a material controller or a list of material controllers as one of its variables, then Unity will be able to automatically serialize any of the material controller's serializable fields to the mono behaviors inspector. So let's start by declaring our inspector assigned variables. Now just to remind you, if I go back to the finished version of the Creeper project and look in the inspector for our switch trigger, you can see that we wish to expose a reference for a project material, for diffuse texture, diffuse color, a normal map, a float for normal strength, a texture for the emissive map, an emissive color, and also a float for the emission scale. So those are the members that we're going to have to declare now. So the first one is of type material, so that we can store a reference to that project material, and I've called this material, remembering to serialize it, of course. Next up, I declare a variable of type texture, which I call diffuse texture. Once again serialized, and this is how we're going to hook up the diffuse texture reference in the inspector. We also saw a moment ago that we wish to allow the developer to specify a color as well for the diffuse. So we will declare a variable of type color, which I'll call diffuse color, and I'll set that to white initially. And then we also have the normal map and the normal strength. So that's going to require a texture again and a float. So I declare a texture called normal map, and I also want to declare a float called normal strength. And the normal strength property will allow us to specify to the standard shader how we would like to scale the contributions of the normal map. Okay, next up we have all of the emissive stuff. So we're going to need a texture to store the emissive map. As you can see, it's another serialized field of type texture, which I've called emissive texture. We also want to expose an emissive color, which we saw our switch trigger uses. So I will declare another variable of type color called emission color, but we'll set the emission to black by default. Okay, so by default, it won't be emitting anything. And finally, we'll declare a float called emission scale. Now we set emission scale to 1 by default. The emission scale, unlike the rest of these material properties, is not actually sent into a variable inside the shader. It's more of a UI concept. In Unity Standard Shader, the color picker at the time of writing was an LDR color picker, which means you were unable to specify HDR colors using the color picker. So the way they got around this was by having a separate UI slider called emission scale, where you could scale up the color before it was sent into the shader. So the standard shader knows nothing about emission scale, it just gets an emissive color. But the standard shader UI makes sure that the emission scale is multiplied by the emissive color before it is set as a shader property value. Okay, so that's all of the serialized fields done for our material controller. And if we were to serialize this to a MonoBehaviors inspector now, it would look exactly like the material controllers we saw in our generic switch triggers inspector. So let's now move on to the protected variables. Now, one of the things that the material controller is going to do in its onStart function is it's going to need to back up all of these values and store them somewhere so that it can restore these values when the material controller is deactivated or reset. So where should we store all of these values? Well, the obvious choice is in another internal material controller. So we're going to create a protected variable of type material controller called backup. Now, this backup material controller is really just being used as a data container, okay? It's an internal material controller, so it's never going to have its start function called or its activate function called by some parent MonoBehaviors script. We'll set this to null by default and it will be allocated in the material controller's onStart function. The next protected member I'm going to declare is going to be a boolean, which I've called started, and it's set to false by default. Now, for obvious reasons, we never want the onStart function of a material controller to ever be called more than once. That's because it's in the onStart function that all of the material properties will be fetched from this material and stored in the backup so that when we exit play mode or we deactivate the material controller, all of those properties can be restored. So this should only ever happen once, because if it got called again and again and again, the backup would have its values overwritten by those extracted from the material, which may no longer be the ones that were set in that material when we first entered play mode. Finally, although we're not going to use it in this lesson, I'm also going to create a public property that will let external scripts get a reference to the material controller's underlying material reference. You're going to see in the next lesson, when we create our computer system puzzle, that script uses a material controller as nothing more than a backup mechanism. It doesn't use its activate function. It just uses it and its onStart function to make a backup of the material's startup properties, so that when code elsewhere in the script starts swapping textures and colors around, the material controller will reset itself when exiting play mode. So you're going to see it used in that way as well in the next lesson. So here is our property. I've called it material with a little m. returns a material reference. It's just got a getter that returns our underlying material. So let's now write our onStart function. I called this function onStart instead of just start, just so that we didn't get confused and think that this was the same as the start function of a mono behavior. If we forgot and assumed that this was also a mono behavior, we might assume that Unity was automatically calling the start function on our behalf. Unity is most definitely not calling this onStart function because the material controller is not a mono behavior. The first thing we'll do inside the start function is we'll check we have a valid material reference. If it's null, or if this function has already been run once, then we return. We never want this function to be allowed to execute more than once. In the next line, we set started to true, so that if onStart should ever get called again, it won't be allowed to run and it will abort from the function on the previous line. So next up, we need to get this material. We need to extract all of the properties that this controller might change, and we need to store them in the backup material controller. So let's first of all allocate a new material controller. So as you can see, I say backup equals new material controller. We now have a place where we can store all of the properties we're about to extract from our material. And to extract those properties, we can use the material classes getTexture, getColor, and getFloat methods. In order to write these functions, you do need to know what the underlying names of the shader variables are in the standard shader, but fortunately I do, and I will take you through them. So first up, we want to extract the diffuse color and store it in the diffuse color member of our backup material controller. So I use the material classes getColor function, and the name of the diffuse color, or the albedo color, in the standard shader is color with a capital C and an underscore like so. Next up, we'll get the diffuse texture by using the same means, but this time using the material classes getTexture function. The diffuse, or albedo texture, in the standard shader is a variable called main_tex. As you can see, M and T are capitalized and it has an underscore. Next up, we'll fetch out the emission color. This is a variable called emission color with an underscore in the standard shader, and I use the material classes getColor function to fetch that color and store it in the emission color field of our backup material controller. We always set emission scale to 1 for the backup, and that's because, like I said just now, emission scale is not a shader variable, it's more of a UI concept. So whenever we fetch the emissive color out of a material, it's already pre-multiplied with any emission scale that we may have set for it via the standard shader inspector. So when we wish to set an emissive color, we take the emissive color that we've set and multiply it by the emission scale, and then we set that multiplied color as the value of the shader variable. But when we get the emission color, it's already been pre-multiplied. Let's now get the emissive texture by using the material classes getTexture function, and the standard shader stores the emissive map in a variable called emissionMap with an underscore, and as you can see, we store that in the emissive texture slot of our backup material controller. Let's now get the normal map and the normal scale. So we'll use material.getTexture again, but this time we will fetch the normal map, which in the standard shader is called bumpMap with an underscore, and we'll store that in the normal map slot of our backup material controller. And I'll also fetch the normal strength from the standard shader. In the standard shader, the variable is actually called bump scale with an underscore, and it's a float. So to fetch it, we need to use the materials getFloat function. And as you can see, we store the result in our backup material controller. We've now fetched all of the properties out of the material and stored them safely in our backup material controller, so that if we ever need to reset this material controller, such as when we exit the scene or exit the application, we can fetch these values out of the backup material controller and send them back into our material. The next thing we need to do is register our material controller with the game scene manager. Now, we've done things like this lots of times before. We have our player info objects that register themselves with the game scene manager, and we have our AI state machines that register themselves with the game scene manager. And we're going to create, once again, another registration function with the game scene manager that this time is going to allow us to register material controllers. So let's put the line in now that's going to register it, and then after this script is complete, we can then jump over to the game scene manager and we can add the registration function there. So I check I have a valid game scene manager instance in the scene, and if I do, I call its register material controller function. This takes two parameters. The first is the integer, which will be the key in the material controller dictionary inside the game scene manager, and for my materials I use the instance ID of the underlying material reference itself, okay? And that's really important because it means if we have multiple material controllers all sharing the same material reference, they won't each get a chance to duplicate themselves in the game scene manager's material registration list. Only the first material controller that registers this material with the game scene manager will get registered. And that is the first material controller that registered, so its backup should contain all of the properties of the material just prior to entering play mode. And as the second parameter, of course, we send in a reference to this material controller object. Let's now move on to the activate function, which is going to be called by our scripts when it wishes us to take all of these properties that we've assigned to the material controller via its inspector and apply them to the variables of the shader being used by this material. So the function is called activate, and it takes a boolean describing whether we wish to activate or deactivate the material controller. First, we'll check that we have definitely called the onStart function. If we haven't called the onStart function, we don't allow this function to run. So you can see I say if the started boolean is not set to true, or of course if we have an invalid material reference, then we just return and we do not activate. But if we have chosen to activate the material controller, then we just need to, using the material class's methods, call setTexture, setColor and setFloat to send all of these properties into the respective variables in the material shader. So it looks something like this. But if we haven't activated it, then we've deactivated it. So we need to do all of this again, but this time, instead of sending in the inspector assigned variables, we fetch these properties all from the backup that we made when our start function was run. So it looks like this. And that is our activate function complete. So the next function I need to create is the onReset function, which is pretty much an exact duplicate of this code here. I'll literally just copy and paste it. And the onReset function is going to be called by the game scene manager in its onDestroy function. Okay, so when the game scene manager realizes that it's going to be destroyed, which in the case of Creeper means that we are exiting the game scene, or we were in play mode inside the editor and we've decided to exit play mode, the onDestroy function of the game scene manager will iterate through all of the material controllers that have been registered with it and will call its onReset function. And the onReset function will basically just do this, setting all of the material properties back to those stored in its backup. We'll first check that we do have a material controller called backup, which should always be the case, and that we also have been assigned a reference to a material. And then, like I said, we will just do what we've done above here, setting the color, the main texture, the emissive color, the emissive map, the bump map, and the bump scale using the properties from our backup material controller. And that is our onReset function complete. Let's now add one more function called getInstanceID. Not sure if I'm going to need this or not, but what I'll do is I'll have a getInstanceID function which will just return the instance ID of the underlying material, because we know that it's that ID that we are using to store references to the material controller in the game scene manager's material registration list. So I'll say, assuming we have a valid material, return material.getInstanceID. And that is our material controller done. We can't use it or test it yet because we need to implement the registration system inside the game scene manager. So we will do that next. So here I am now inside the game scene manager script, and we've done this type of registration stuff lots of times before now. So I'm going to scroll down to where my other 3 registration dictionaries are, and I'm going to declare a new dictionary, but this time storing an integer and a material controller reference. So as you can see, it's a private dictionary called Material Controllers, where the key is an integer, which as we've seen will be the instance ID of the material controller's underlying material. And as the value stores a reference to the material controller class that is registered here. So let's now create the registration function. Nothing new here. It's a public function with a void return type, and I've called it register material controller. Takes as its first parameter the integer key, which as we've discussed will be the instance ID of the material controller's material. And as the second parameter we pass in the material controller reference. So inside the function, and this is very important in this particular case, we make sure that that material instance ID is not already contained within our dictionary. And if it is, we don't want to overwrite it. We just want to ignore it because it means we've already got a material stored there. And it also means that the material stored there will be the very first material that registered itself with the game scene manager. And that's exactly what we want. But assuming there is no key in our dictionary which matches the material instance ID we've been passed, we store our material controller in our material controllers dictionary using the material instance ID as the key. Now normally when we create a registration function, we normally create a getter function. But we don't need that for the material controller. What we do need in the game scene manager though is to implement the onDestroy function. The onDestroy function will be automatically called by Unity when the game scene manager is destroyed. And it's in this function that we're going to tell all of the registered materials in our material controllers dictionary to reset their properties from their internal backups. So this is called onDestroy. It's another one of Unity's magic functions which will be called automatically by the engine. And I just need to create a for loop that's going to iterate through each key value pair in my dictionary. And I do this by saying for each, and then I specify the key value pair type. So we're looking to get key value pairs from my dictionary with integer keys and material controllers as the values. And in each iteration of the loop we'll be given a key value pair which I store in a local loop variable called controller. And in each iteration of the loop, we'll get the value of the key value pair, which remember is the material controller reference, and we call its onReset function, which we saw a moment ago is the function that inside the material controller sets the material properties back to what they were when we first entered play mode. And that is our game scene manager complete. So let's now go back to the editor and just create a temporary script to test that this is all working, and also check that we haven't got any errors. Okay, so right in the top assets folder, I'm going to create a temporary script. We're going to delete this in a minute, and I'm just going to call this mattest, okay? And I'm going to open this up in MonoDevelop. I'm going to delete the update function, and I'm going to create one, I'll just make this public for now, public variable of type material controller, and I'll call this controller. I'll set it to null by default, and in the start function, we will call the controllers onStart function. Like so. I'll save that off. I'm not even going to bother testing the activate because it's obvious that's going to work. I just really want to make sure that the registration system in the game scene manager is working. So what we'll do is we'll add this script to a game object. Anything would do. So for now, I would just add it to, let me just create a new empty game object. I'll just leave it left at game object for now. I won't even change the name. I'll drag our mattest script onto it. And if we open up the controller dropdown now, hey, look, there is our beautiful serializable material controller. So what I want to do now is I'll just lock that for a moment, all right? And I'll choose a material, this wall material here. What is it? Actually, I'll unlock the inspector. Now I've selected this wall material. I just want to see what materials we've got here. We've got prop wall panel 1. Is that it? No. Ah, there it is. It's called Tile Wall Concrete A Matte. A nice, easy to remember name. Okay, so now we know what material it is. Let's now select our game object that we just added to the scene with our test script on it. And let's drag that over into the material reference. Okay, so that material is now being referenced by our material controller. We won't touch anything for now, all right, because we're not even going to activate this material controller, but we'll just change it at runtime. So I'm going to press play, right? Then I'm going to call up the project view. I'm going to select that material, and I'm going to do something like really crazy with it, like set the wall to red, okay? Now, even though we haven't activated the material controller should still have backed up this material's values. So when we exit play mode, it should restore it back to what it was. Hey, look at that. And it did it perfectly. So let's test it again. Let's press play. And this time, let's do something like assign it some weird texture. So I'm going to assign it the computer lockdown activated texture as its albedo. Hey, look at that. And once again, when we exit play mode, it resets itself back. So as you can see, the material controller is a pretty cool class in its own right, and it all works just fine. So let's now delete that game object from the scene that we temporarily just added. And let's go up into our root assets folder and let's delete that mattest script because we are never going to need that script. Okay, so now what we need to do is we need to write our generic switch trigger script. So I'm going to drill down into my scripts folder and into my interactive items folder, and I'm going to create a new C# script, and I'm going to call this interactive generic switch. Generic. As you can see, I am changing the names slightly from what I called them in the original Creeper prototype. I want all of my interactive items that are based on the interactive foundation, to have the word interactive, and then I know what it is, and I know it's an object that will be responsive to the character manager's raycast. So let's now open that up in MonoDevelop, and let's change the base class from MonoBehavior to interactive item, because it is going to be derived from our interactive item base class. It is, of course, part of our interactive item framework. And for now, I'll just delete the start and update functions. We do need a start function, I believe, but we'll add that as and when we need it. Okay then. So this interactive generic switch is going to need to use some custom types. In particular, it's going to need to have some custom classes to help it represent data that needs to be sent into an animator. If I go back to the final version of the Creeper game and once again select the switch trigger so that we can see the configurable entities section in its inspector. Oh, and by the way, these bold statements here like game state management, message, activation parameters, operating mode and configurable entities, you'll see in a minute that we can mark up our inspector in this way by using the header attribute. And it's really cool because it allows us to divide lots of data into groups that just makes it more digestible, I think, to someone using our component. But in particular, I want to look at the animation. And you can see that in the case of our animations list, each element in there is a custom class. And it needs to store a reference to an animator component, but then it also needs to store a list of animator parameters, right? And then each element in the animator parameters list is also part of a custom class that has a type. As you can see, we have bool, trigger, int, float, and string. Now, although I've defined all of these, only bool is currently supported, okay? I haven't gotten around to implementing the other types yet, so that might be something you have to do yourself if you don't want to wait for me to do it later on. But so far I've been able to just do everything with bools, so I haven't needed to implement anything else. And the reason for this really is not because it's difficult to do. It's incredibly easy to send data into an animator. It's just I haven't really thought of what good default values should be for other parameter types. So in the case of a Boolean parameter that is set to true when this is activated, well then we know that when it's deactivated it should be set to false. But that's not true for an animator parameter that's a float. If something has a float value of, I don't know, 10.96 when it's activated, do we necessarily know for sure that we want that set back to 0 when the switch is deactivated? So one way you could get around this is to specify both deactivate and activate parameters for all of the animator parameters in these lists, but to me it seemed a step too far, but you're free to expand this script how you want. So there's two custom types we need to create here, right? We need to create an animator parameter custom type, which has three members, a type, a name, and a value. We also need to create this kind of animator configurator custom type that stores a list of anim parameters and also a reference to a animator component. So let's start by creating these support classes. So I'll start by defining an enum that defines all of the various parameter types that we can find in an animator, at least at the time of recording this video. So I've called this public enum animator parameter type, and it contains the members trigger, bool, int, float, string. Okay, and this is what's going to show up in the inspector in this drop down here when we're configuring our parameters. But like I said, at the moment only bool is supported. So now I'm going to create the class that's going to represent the animator parameter. Okay, so I will call this animator parameter, and obviously we want this to show up in the inspector of a mono behavior, so we'll make it system.serializable. And as its first member, we will have an animator parameter type, and by default we'll set it to animator parameter type bool. And just to remind you, if I go back to the finished version of the Creeper game again, you can see indeed that the first element inside an animator parameter is the type, and because it's an enum it will show up in the inspector with this nice little drop down. So okay, so the second member of our animator parameter is the name of the parameter in the animator that we want to set. So this is just a string called name, which we set to null by default. And of course the third member is another string, this time called value. So that's our animator parameter class done. Let's now create the animator configurator class, which is the parent class that contains a list of animator parameters and also a reference to an animator component. So I will call this animator configurator. Once again, we'll make it system.serializable so that it shows up in the inspector. And for its first member, we'll declare an animator, which I've just called animator, and that's where via the inspector we will hook up a reference to, for example, our button animator component on our power generator. And then it contains a list of animator parameters, okay, that class we just created. And that's basically the animator configurator support class done. As you can see, it's just a reference to an animator and then a list of all of the instructions, if you like, all of the parameters and their values to set in that animator when this switch is activated. Okay, so now we're ready to work on our generic switch. So the first thing I'm going to do before I declare any variables is I'm going to use the header attribute, and I'm going to pass the string to this attribute of game state management. And going back to the finished version of the Creeper game again, you can see that this comes up in bold in the inspector, and whenever we use the header attribute, it also puts a little space between the variables that were declared before it. So it's a way of decorating the inspector and also grouping our members together into logical groups. So in the game state state management section, we're going to declare the 3 state lists. Remember, each one of these is just a list of game states, and we've already created the game state class. So let's go now and create the lists that belong in the game state management section of our inspector. So I will create a list of game states, and remember the game state class we created a while ago. If I call up the application manager, it looks like this. It just has 2 strings as members, a key and a value. So that's where we get to store things like power as the key and true or off or whatever you want as the value. So going back to our generic switch, we now have declared a list of game states to store all of the states that are required in order to activate this switch. Next up, we'll do pretty much the same thing again. We'll declare another list of game states, but we'll call this the activate states. Now, these are the states that will be set when this switch is activated. Okay, so when we activate this switch, the activate function will iterate through every game state in this list and set it. And finally, we have the deactivate states. And just to switch back to the final version of the inspector, there are those 3 state lists. That's exactly how they'll show up in the inspector. 3 lists of game states. So next, we're going to work on the message section. And once again, I use the header attribute so that we put a little bit of spacing between these 3 lists in the inspector. And we also see in nice bold text the word message above the variables that we're just about to declare. And if we go back to the finished version of the Creeper game again and look at the inspector that we're trying to create, in the message section we create 3 text boxes. Let's create those now. And now these are going to be just strings, but with each string I'm going to also mark them up with the text area attribute so it shows up as a text box in the inspector. So you can see this is a string called state not set text. Next we have another string called state set text, and then the third string is called object active text. So this is the string that will be sent to the HUD when the required states have not been met. This is the string that will be sent to the HUD when the required states are met but the object is not active, and this is the text that will be sent to the HUD when the object is active. And that is our header section done. So next up we have the activation parameters, and the first 2 members will both be floats where we get to specify the activation delay and the deactivation delay. The object activators, the object deactivators, and the material controllers when we activate a switch all happen after the activation delay. The exception is the animations lists. The animation parameters are executed prior to the activation delay. I just found that that makes sense because when you press something like a button, you want to see the animation happen immediately. It's normally while you're waiting for that animation to play out that you want the activation delay before things happen, such as the lights coming on or a horde of zombies being spawned. So we can set the activation and the deactivation delay separately. That's cool. Next up, we will declare an audio collection called activation sounds. In this audio collection are the sounds that will be played right away when the object is activated. And in bank 0 will be the activation sound, and in bank 1 will be the deactivation sound. So we can have a different sound for activation and deactivation. And after testing this script in lots of different situations, I found that the most useful way for this to work was that when we activate the switch, the activation sound plays straight away. And when we deactivate the switch, the deactivation sound happens after the deactivation delay. That's just what I found to be useful. But you can change this if you want. Next up, we need to allow the developer to specify the audio source reference that the audio collection should play through. We don't want to make any assumptions that we want this to play as a one-shot sound, as that is often not the case, and we often don't want to risk having multiple sounds played as one-shots overlapping one another. So next up we have the operating mode section. First I'm going to declare a boolean called start activated, which as we saw in the last lesson, this allows us to specify whether we would like the switch to start activated rather than the default, which is starting deactivated. And I also declare another boolean called can toggle, which is false by default, but if set to true means that we are able to activate and deactivate this switch multiple times, as many times as we like. If this is set to false, then you can only deactivate it if it's activated at startup, or activate it if it's deactivated at startup. So you only get one interaction with it. Okay, so next up we have the configurable entities section. Remember, this is the section where we declare all of our animations, our material controllers, our object activators, and our object deactivators. So first up is the animations. So we will declare a list of animator configurators called animations. Remember, the animator configurator is that class we created a few moments ago, which contains a reference to an animator component and a list of animator parameters. So we're storing lists of animator configurators, right? And that's why we are able to send multiple parameters into an animator, and we're able to do that for multiple animators in our level as well. So that's all we have to do. Because all of those subclasses are serialized, just declaring this list will make all of that stuff show up in the inspector. Next up, we have to declare a list of material controllers. So as you can see, I declare a list of material controllers called material controllers. Then we have the object activators list. This just needs to be a list of game objects, which I've called object activators. And of course, we also need a list of game objects describing the objects that we wish to deactivate when this switch is activated. So I call that object deactivators, which is once again just a list of game objects. Okay, so let's now go on to the private and the protected variables. So this is going to use a coroutine like all of our interactive items seem to. So we'll create a protected IEnumerator member called coroutine, which will be used to store a reference to the coroutine function. We will also declare a boolean called activated, which will keep track of whether this switch is currently activated or not. We'll set it to false by default. And we'll also declare another boolean called first use. This is needed when we have set the can toggle boolean to false, because that means that we can only use this object once. We can either turn it off or turn it on. So whenever we activate an item, we will always set first use to true, so that we know if ever we try and activate an item again, if can toggle is false and first use is true, then we know we can just return from the activation function. We're not allowed to activate it again. And that is all of the variables declared for our generic switch class. Now obviously it doesn't do anything yet, but if we were to drag an instance of this script onto a game object, our inspector would indeed look as it did in the finished version of the Creeper game, with all of those lists and text boxes where we can set all of the things such as animation parameters, material controllers, and lists of game objects. So all we have to do now is write the functions that's going to make all of this stuff do something. So let's start with the start function. Remember, this is an interactive item derived class, so we need to override the start function, but it's also very important that we call the base class implementation of the function, because it's in the base class version of the function that the interactive item registers itself with the game scene manager as an interactive item. If we forgot to call the base class implementation, then our character manager would never detect that the ray has been cast through it. Next up, we will iterate through every material controller in our material controllers list and make sure that for each one we call its onStart function, giving that controller a chance to back up its properties and register itself with the game scene manager. Inside each iteration of this loop, I say if we have a valid reference to a material controller at this location in the list, then call its onStart function. Next up, we want to iterate through all of the game objects in the object activators list. Those are the objects that need to be turned on when this switch is activated, and we need to turn them all off at startup. Now I know what you're thinking. You're thinking, well yeah, but what if we've chosen to start this switch activated? Well, you're going to see how we get around that at the moment. So for now, while we're covering this bit of the start function, assume that all switches start deactivated, and therefore we need to deactivate all the object activators and activate all of the object deactivators. So inside each iteration of this loop, as long as we have a valid reference to a game object stored in that element in the list, we call it setActive function, passing in false. So we turn off the game objects. Remember, these are the objects that need to be activated when the switch is activated, and at the moment we're pretending that all switches start deactivated. So now we need to do the reverse for the objects in the object deactivators list. Because we're pretending that this switch is starting deactivated, we need to activate all of the object deactivators. So once again, I'll create a loop that's going to iterate through all of the game objects in the object deactivators list, and for each one, call its setActive function, passing in true so the object is activated. Now this is where we're going to do the flick. Remember, we have a boolean called startActivated, which allows us to describe to this switch whether we wish it to start in an activated state. At this point in the start function, we have assumed we wish it to start in a deactivated state and have configured all of the objects as such. What we're going to do now is use the activate function, which we haven't created yet, to activate it if the startActivated boolean is true. So it looks a bit like this. So this activate function is the function that's going to be called by the character manager when it detects that this object is under the crosshair and the player has pressed the use button. If we have chosen to start activated, then we will activate it ourselves from inside our start function. Now remember, the parameter to the activate function as defined by the base class is a character manager reference, but we don't need a character manager reference in our activate function, so I just pass null. However, one of the things that the activate function is going to do is it's going to set first use to true. So if this is not a can toggle object, the activate function would never be allowed to be called again. However, this isn't a true activation. This is a hidden activation that we're doing ourselves to start the object in an active state. So when we call the activate function, the first use boolean will be set to true, which means that when we get into the game and we try and actually activate the object, if it has been set so that it can't be toggled, we're going to be denied from using it because it's going to think it's already been activated. So we just make sure that after we've done an internal activation, we set the first use boolean back to false so that the activate function can still be called one more time. But remember, this only applies in the case where this is not a can toggle object. And that is our start function complete. I'm now going to write a helper function. You see, one of the things that we're going to need to do when we activate this switch is iterate through all of the activate states here in our activate states list and set them in the application dictionary. So I'm going to put that in its own little helper function called set activation states. The first thing this function does is tries to get a reference to the application manager, because remember, the application manager contains the game state database, and if the application manager cannot be found in the scene, we simply return false. Our scene has been configured incorrectly. However, if that's not the case, we need to check whether we are activated or deactivated. If we're activated, we need to set the activate states. But if we're not activated, we need to set the deactivate states. So if we're activated, we will loop through each game state in our activate states, and for each one we will call the app manager's set game state function, passing in the key of our game state as the key and the value of our game state as the value. However, if this switch is not in an activated state, then we wish to do pretty much the same thing again, but not with the activate states, with the deactivate states. We'll create another for each loop that iterates through this time all of the game states in the deactivate states list. And for each one, we will call the app manager's set game state function, passing in the key and the value of the game state into the app dictionary. And that's our set activation states function done. Another helper function that we wish to create, we'll write a little helper function called requiredStatesSet. It returns a boolean, and if this returns true, it means all of the required states are set as they should be in the game state dictionary, which means we can activate the switch. But if this function returns false, it means the required states aren't set and the switch is not ready to be activated yet. So the first thing we'll do is get a reference to the application manager in the scene, and if one can't be found, return because our scene has been configured incorrectly. Otherwise, we will set up a for loop that's going to iterate through all of the required states. In each iteration of the loop, we will get the state that we are currently processing. We want to find out whether this state and its value matches the state and value in the game state dictionary. If it is, then we know that at least this state has been set and we can move on to processing the next state. But if we find at any point while processing this loop a game state that doesn't match its correspondent in the application manager's game state dictionary, well, then we know that the required states are not set. So after we fetch the game state, we will use the application manager's getGameState function, passing in the key of our game state. Remember, that's the name of the actual state. And this function will return the value, which we store in the result. So basically, our result here should match the state's value. So we'll say if the result is null or empty, or if the result doesn't equal the value of our game state, but then we found that the required state doesn't match its correspondent in the game state dictionary, and we return false immediately from the function, we cannot activate this switch yet. However, if that loop iterates through all of the states and doesn't return false, it means all of the states match and we return true. So with the requiredStatesSet function written, we can now write the getText function. Remember, this is the function that is called by the character manager to get the text that needs to be displayed on the HUD. We need to override this from the base class. The first thing we'll do is just check that our trigger switch component is enabled. If it's not, then some of the data it needs may not be set up and initialized, so we'll just return an empty string. But failing that, we'll first check whether this switch is activated, because if it is activated, then it's really simple. We just return the object active text. Remember, if we go up to the inspector assigned variables, the object active text is the text that is returned when the object is activated. What we need to do now, though, is carry on with the function. In the case where the object isn't active, find out whether we need to return the state set text, meaning all the required states are set and the object is ready to be activated, or the state not set text, which means the required states are not set yet. So we're going to use that function we just written. As you can see, I create a local bool called required states, and I assign to that the value returned from our requiredStatesSet function. All right, so if all the required states are set, this boolean will be true, otherwise it will be false. And if the required states are not set, we will return the state not set text. Otherwise, we will return the state set text. And that is our getText function for our generic switch done. Okay, so next up we're going to do the activate function. Remember, the activate function needs to be overridden from the base class, and it takes as its single parameter a character manager reference, although this script won't use that parameter in any way whatsoever. So as with the other functions we've just written, the first thing we need to do in the activate function is check we have a valid reference to the application manager, and if we haven't, return false because our scene has not been configured correctly. Failing that, we need to figure out whether the first use boolean has been set to true, which means the activate function has already been called within the game. And if that is true, and this is a not can toggle object, then we need to return we're not allowed to use this switch again. So next up, I need to figure out if we're not activated, can we activate it? So I say if we're not activated, then let's once again call our required state set function, which the return will be set to either true or false depending on whether we can or cannot activate this switch. If the result we got back from that function was false, the required states aren't set, we return immediately. We are not allowed to activate this switch yet. The required states are not set in the game state dictionary. So outside of this not activated conditional, we have code that is going to execute irrespective of whether we've called the activate function to activate or deactivate the object. So the first thing we need to do is toggle or flip the activated state of our switch. So if it was previously activated, if activated equals true, it now gets set to false. But if it was previously false, it now gets set to true. And we also need to set the first use boolean to true. This is our way of recording that we have now had a legitimate interaction with this script from within our game. And if this is an object that cannot be toggled, then it means that the next time we try to call the activate function on this trigger, we will abort the function prematurely on this line here. So remember I said a few moments ago that in the case of activating the switch, we wish to play the activation sounds right away. But in the case of deactivating the switch, we want the deactivation sounds to play after the deactivation delay. So at this point in the function, I need to play the activation sound, but only if we are activating the switch. Because like I said, the deactivation sounds only get played after the delay. So you can see I create this conditional that says, assuming we've been given a valid reference to an audio collection and we have just activated the switch, then we will get a random clip from our audio collection. Notice I use the activated boolean to say if we're in an activated state, then use bank 0. Otherwise, we want to play the deactivation sound, so play bank 1. So that's pretty cool, but completely unnecessary here. I've just noticed that that is obviously something that's been left over, a bit of legacy code there. It doesn't hurt it, but I could just leave 0 in there because we never step into this code unless we are in an activated state. So I could just say activation sound 0 here, but I'll go and fix that at the end. Remember, bank 0 contains the activation sounds, bank 1 contains the deactivation sounds, and at the moment we're only interested in playing the activation sounds. However, if we weren't able to get a valid audio clip to play from our audio collection's first bank, we return. However, if that's not the case, we need to check we have been assigned a valid audio source to play this sound through. Remember, the audio source is also assigned via the inspector. So what we need to do, if we have got a valid audio source, is we need to assign all of the properties to it. So we'll assign our clip to play that we just fetched from our audio collection to the clip property of the audio source. We'll take the volume from our audio collection and assign that to the volume of the audio source. We'll do the same with the spatial blend. We'll do the same with the priority. And then what we also need to do is we need to make sure that we assign the audio mixer group to the audio source as well. Now, normally when we're dealing with our audio manager, we just pass in the name of the audio mixer group. But in the case of the audio source, it actually wants an audio mixer group object. And you may remember from many lessons ago when we created our audio manager, we actually have a function called get audio group from track name. And this will actually return the audio mixer group object, which we can assign directly to the audio source's output audio mixer group property. So you can see I call the audio managers get audio group from track name, and as the track name I send in the audio group string of our audio collection. With our audio source all set up to play this activation sound correctly, I then call the audio source's play function. So next up, we're going to execute a coroutine that's going to finish off the rest of the activation procedure, including the activation and deactivation delays. However, I don't want multiple coroutines running, so if our coroutine is already running, I call stop coroutine. Then I assign to our coroutine variable a function we're going to create in a minute called doDelayedActivation, and then I call the doDelayedActivation function as a coroutine using Unity's start coroutine function. So finally, let's do the doDelayedActivation coroutine. our do-delayed activation coroutine returns an IEnumerator. The first thing this function does is iterate through all of the animator configurators that we have in our list. It needs to send all of those parameter lists to all of their various animators. Notice though that we do this at the top of the coroutine and not after we've yielded for any delay. So basically, even though I moved this code into the coroutine just to tidy up the activation function a little bit, it could have been above the start coroutine function in the main activation function, as the animator configurators are being processed pre-delay. So in each iteration of the loop, we'll get one of our animator configurators from our list. And assuming it's not null, we need to iterate through each of the animator parameters that it has defined. And for each parameter, I need to figure out what type it is and act accordingly. At the moment, as I said earlier, I only support Boolean types, so that's going to be pretty easy. But I've put the switch infrastructure in there anyway, so that you can easily add the other types if you want to. So you can see I use the type member of the parameter that we are currently processing in this iteration of the loop, where the type is animator parameter type bool. We take the value that we've assigned to that parameter. Now remember, in our animator parameters class up here, the names and the values are stored as strings. We want to get that into its Boolean form. And we can do that by using the bool class's parse function. We pass it a string and it does its best to turn that into a Boolean variable. Obviously, if you put rubbish in there, you're not going to get back what you want. But if you put true or false in there, you're going to get a proper Boolean variable as the result, which is set to either true or false. So as you can see, I create a local variable called Boolean and I assign to that what should be the Boolean returned from the bool class's parse function, sending in our parameter value as a string. So now we have this Boolean parameter. We now need to send it into the animator that is being referenced by this animator configurator. So we get the configurator's animator reference, we call it setBool function, passing in the parameter name that we'd like to set. And you can see that if we are in an activated state, then we send in the Boolean. But if we're in a deactivated state, we send in the opposite of the Boolean, right? So if the activated state was true, then when we're deactivated, we're going to send false into the animator's parameter. And that's one of the reasons I haven't created the other cases yet, because I just don't know what to do for the best in the case of floats and things like that, what the deactivated value should be. And finally, we break from the switch statement because we've now processed the animator parameter. So to paraphrase then, we get our animator configurators list. Remember, each configurator stores a reference to an animator and a list of animator parameters. So for each configurator, we loop through each of the animator parameters and send each one into the animator configurator's animator. Okay, so at this point, all of the animators have been configured with all of their parameters. Next up, we want to do a yield. This is where we're going to do the activation or the deactivation delay, depending on whether we are activating or deactivating the switch. So as you can see, I do a yield return new wait for seconds. And if we're activated, I use the activation delay. And if we're not activated, I use the deactivation delay. After we've paused the execution of this function for the correct activation or deactivation time, it's now time to execute all of the other entities, such as activating our material controllers, activating our object activators list, and deactivating our object deactivators list. So the first thing we'll do is call that set activation states function that we wrote earlier on in this class. This is the function that sets all of the states that should be set in the application manager's game state dictionary when this switch is activated. So in the case of our generator, this function has set power equals true, whereas previously power equaled false. Next up, we wish to play the deactivation sound. Remember, when deactivating, we wish to play this sound after we've yielded for the deactivation delay. You don't have to do it like that. I just found that in most cases, that made sense. So unlike in the activate function, where I said only play the sound if we're activated, in the coroutine, we're only going to play the sound if we're deactivated, because obviously if we're activated, we've already played the activation sound before the coroutine was called. So I say if we have a valid reference to an audio collection and we're not activated, then get an audio clip from our audio collection. Once again, I've used that if activated, use bank 0, if not activated, use bank 1, but that is completely superfluous in this particular case because we know that we are definitely deactivating the object here, so that should be just 1 in there. But it doesn't hurt it, this will evaluate to the correct result anyway. The reason why I originally did it like this is I didn't originally play the activation deactivation sounds at different times. They both used to happen after the yield. So I would have to say, are we activated or are we deactivated? And if so, what bank do we play? But as we've split up now, activation and deactivation sounds kind of different points along the timeline. It's no longer necessary to do this test here. So assuming we have a valid reference to an audio source, we have a valid audio clip to play, we do all that stuff that we did before, assigning all of those properties to our audio source, and then calling the audio source's play function to play the actual deactivation sound. Okay, so next up, we now need to iterate through all of our object activators, and we need to activate them if we're activating the switch, or deactivate them if we're deactivating the switch. So you can see the first thing I do check is that we do have some elements in our object activators list. And if we do, I set up a for loop to iterate through each one. So in each iteration of the loop, I check that we have a valid game object in that slot in the object activators list. Then if we have, I call it setActive function, passing in our activated boolean. So if we are activated, we pass in true, activating the object. But if we're deactivated, we pass in false, deactivating the object. Okay then, so that's all of the object activators process. Now let's do the object deactivators, which needs to work in exactly the opposite way. So as you can see, I check I have some elements in the object deactivators list. I then set up a loop to iterate through each one and process each element in that list. And in each iteration of the loop, if I do have a valid reference to a game object at that location in the list, I say object deactivators.setActive, and this time I send in not activated. All right, so the exact opposite happens. When we're activated, the object deactivators get deactivated because false gets sent in. But when we're deactivated, then not deactivated equals activated, and all the object deactivators get activated. Okay, so next up we need to process our material controllers list. So we will iterate through each material controller in our list, and assuming we have a valid reference to a material controller at that element in the list, we will call the material controller's activate function, passing in activated as its parameter. So once again, just like the object activators list, if the object is activated, we're going to be activating the material controller. If the object is not activated, we're going to basically tell the material controller to reset itself back to its original state. And that is our interactive generic switch done. So let's save that off, go back to the editor and see how many errors we have. Yes, we do have some errors. Okay, so let's have a look what I've done here. Well, there you go. Inside the set activation states function, which is supposed to have a void return type, I'm trying to return false. And of course, I just need to return. I think I've done that down here as well, haven't I? Damn those copy and paste errors. So in the activate function, I'm also trying to return false, even though the function's got a void return type. And let's save that off, see if that's fixed all of the errors. Hopefully it has. Okay, well, it's fixed all the errors, and the last thing I'm going to do is I'm just going to go down to the activate function, and in the case where we're playing the activation sound, I'm going to get rid of that and just hard code in there bank 0, because bank 0 is where activation sounds are stored, and go down into our coroutine, and in the case where we are deactivating the object, get rid of that conditional and just put 1 in there. The conditional is just a waste of processing power. Okay, so we now have all of the scripts we need to make this generator work. So now it's time to add it to our generator object and start configuring its inspector properties. So back in the editor, let's select our generator game object in the scene hierarchy. Open it up, right-click on the generator parent object and choose to create a new 3D object of type cube. Let's rename this switch trigger. Selecting the inspector tab, let's also assign it to the interactive layer. I'm now going to move this cube into position, and then I'll zoom in on the inspector and you can pause the video and see the exact position at which I place this object. As you can see, I have positioned it at x equals 0.229, y equals 1.103, and z equals minus 1.55. Of course, this is going to be the interactive trigger that our character manager's ray intersects. It's on this object that we're going to need to add our interactive generic switch. I'm going to turn off the mesh renderer, and then I'm going to resize the box collider because it looks a little bit big at the moment. I'm going to once again pause the video and set the size and the center of this thing so it's how I want it to be. Looking at the box collider, you can see I have the center at x equals 0, y equals 0, and z equals 0.28, and the size is x equals 0.55, y equals 0.73, and z equals 1. I'm going to set this as a trigger, and then I'm going to remove the mesh renderer and the mesh filter. So I just have a box collider on the interactive layer. I'm now going to add our interactive generic switch script, the one we just wrote. And wow, look, that inspector does look exactly how we expect it to look. So we don't have any required states for the power generator, but we do have some states that we wish to set when the generator is activated. It's only one, isn't it? We want to set power to true. Let's create one element in the activated states list with a key of power and the value to true. So when this switch is activated, power will be set to true. We also said that when we deactivate the switch, we wish power to be set back to false, and we also want lockdown to be set to true. Remember, I said in the last lesson that setting lockdown to true was just a personal choice of mine, as I thought it was pretty cool that if you turn the power off, you essentially reboot the machine and undo any lockdown that you might have previously deactivated. So we will set power to false, and we will set lockdown to true. That's all of our states set. The state not set text is not going to be used by this script as we have no required states, so I will just put in there not used. The state set text is the text that is sent to the HUD when all of the required states have been met, but the object is not yet activated yet and it's under our crosshair. So we will say power generator colon not running, and of course the object active text is the text that we want to have set when this power generator is actually active, when the switch is activated. So we will say power generator running. In the original Creeper, I actually set the activation delay to 4.5 seconds. That seems like a long time, but I just got to that by timing things such as how long the engine startup sound took to play. And I noticed that about 4.5 seconds into it, that's when the engine was running normally, and that's when I wanted all of the material controllers and the objects to activate and all that sort of stuff. The deactivation delay, I believe, was left at 1 second. So we also need to assign it the timeline audio source in the audio source member. So this is the audio source that the activation sounds are going to play through. However, at the moment, we haven't got an audio collection with the activation sounds in. We'll do that in a moment. The generator switch does not start activated. Before moving on, let's create the audio collection for our activation sounds. So I'm going to drill down into my sounds folder and into my audio collections folder. And with the audio collections folder selected, I'm going to go to the assets menu and choose to create a new audio collection. And I'm going to call this generator activation. And I'm going to lock the inspector, and I'm going to assign it the scene audio group. I believe the volume was down at about 0.4 in the original Creeper, but of course things like this you just try out, just do it by trial and error. We want the spatial blend to be fully 3D, so we'll leave it at 1. We'll just leave priority at 128, and this needs to have 2 banks. If you remember, I said that the activation sound needs to be in bank 0 and the deactivation sound in bank 1. So there's only going to be 1 sound in each of these banks, so let's make room for those now. So in element 0, which of course is bank 0, we need to assign it our power generator startup sound. So let's go into our scene sounds folder, inside the sounds folder, and drag over the generator starting audio clip like so. And within the same folder, let's select the generator stopping sound, drag and drop that into bank 1, and then we'll unlock the inspector. Then I'm going to select my switch trigger game object. Remember, that's the child of our generator object, which has our interactive generic switch on it, and I'm going to assign it as its activation audio collection, the generator activation audio collection. Now we need to configure the animations list. We only have one animator we want to talk to. Remember, that's the animator on our button, and if I remember rightly, it has a Boolean parameter called activate, which we wish to set to true when this switch is activated. So we will open up the animations drop down and we'll tell it that we want space for one animator configurator, and the animator for this animator configurator will of course be the animator component on our button game object. So that's the button animator, and also we want to create just one animator parameter for this configurator, and it needs to be a Boolean because that's the only one that's supported at the moment. The name is of course activate, that's the name of the parameter in the animator, and as the value we want to send in true. So that's our animator configurator list done. So we should probably test that, shouldn't we? We're not going to hear anything other than the button being pressed in, and we'll hear the engine startup sound, but of course we haven't hooked up any of the object activators or deactivators yet. Okay, you ready? And there you go, and then our activation sound starts. Now, of course, we know what's going to happen is we have a game object here called engine sound, which is going to be enabled as one of the items in our object activators list, which will then take over the sound of the generator from that initial startup sound. But what I should have checked actually was the shutdown sound, shouldn't I? Didn't check that. Let's maximize on view. Let's treat ourselves. Okay, so let's turn it on. And let's turn it off. Ah, bollocks. I forgot to set can toggle to true. What am I talking about? Of course we want can toggle set to true. We want to be able to turn our generator on and off. But the great thing about that was we just got to test that if we don't make this a toggleable object, our code did correctly block us from trying to activate that button again. Okay, so let's go and try it again this time. Okay, power on. And power off. Okay, that all seems to work quite fine. Okay, so let's carry on configuring this. Now, one thing I need to say is that when we looked at the final Creeper game, one of the things that happened when we turned the power generator on was the computer puzzle got turned on in the computer room. Now, we're going to be doing that in the next lesson because we haven't created the computer system yet. But you will remember that once we've created that computer puzzle, adding it to this generic switch is really easy. We're just going to drag and drop the object into the object activators list. And that's all we need to do. So it's not like we have to come back and do any serious work on the interactive generic switch trigger or the power generator object in the next lesson. Okay, so let's now work on the material controllers. I believe we need two, don't we? We need one for the little light on the generator itself, this little thing here. So what did we call that? We called it generator light. So let's select that material like so, and then let's select our switch trigger again. Make room. We actually want two material controllers here, and for the first one I'm going to drag over my generator light material into the material slot of the first element in the list. We can leave all of this how it is, I believe. Actually no, we want to put diffuse color to white when it's activated, and we want to put emissive to green. It was back there, wasn't it? Something like that. And I think we want to set the emissive scale to 1.4, I think, if my memory serves. And we'll do the other element while we're here in the material elements array. Remember, the other thing that we need to animate are the lights, which is that prop battle bus material here. So what's it called? Prop battle bus lights effect. So let's select that in our project view. Go back to our generic switch. And in the second element in our material controllers array, we will drag over battle bus lights effects into its material slot. And we'll just set the emission color to white. We want this to be quite bright, so we'll do an emission scale of 1.66. Now these emission scales don't make a lot of difference visually at the moment, but when we download the post-processing stack, when we're doing the finishing touches to Creeper, you'll realize that scaling the colors up into this range really helps us control what we wish to have bloomed by the bloom filter and what we wish not to have bloomed, because we need to make a definite difference between what is a bright white light and what is just a white wall, whereas of course on our monitor screen white is white. Okay, so should we try this? Let's try it. And let's see if our material controllers do indeed activate. So of course what we should see is, actually let me turn off the off light for the moment, because we haven't done anything with that yet. So it's not going to turn green, and that might hide the fact that our light is working. So I want to definitely see it go from red to green. Okay, so are we ready? And of course there's about a 4-second delay, so it should go green. Yeah, it kind of went green because I got my flashlight on. There you go. Yeah, it's probably too much of a light green. I'll make it a bit of a darker green, but it worked, right? Our material controller worked. And what we should see now is when we go over to the other side of the level, all of the materials of our light should also be white now. Hey, look at that. Cool. They don't look very good without bloom, do they? But it's worked. Of course, when I press stop now, my materials should all resort back to their original values, and they do. Cool stuff. Okay, so selecting our switch trigger again, let's now work on the object activators list, the game objects that are going to be turned on when we activate this power generator switch. So I think, let me just put 4 elements in the array for now. Now, one of the things we know we need to turn on is the light on child game object of the generator. That is the green light. Okay, we've got a red light there at the moment. When I say light, I'm not talking about the physical light material on the generator. I'm talking about, remember, the actual point light that we placed, which is lighting all of the wall up red. We want to enable the light on game object, which is going to light all of the wall up green. So let's drag the light on game object into the list. The other thing that we wish to enable is the public announcement. So let's drag over the public announcement game object. And we also wish to enable the engine sound, right? so that it takes over from the engine startup sound. I think the only other thing we need to enable in this lesson, because we haven't created the computer system yet, is that dynamic lights container, which contains all of the light sources over the other side of the level. So let me select my switch trigger again, and then let me drag over the dynamic lights game object into that object activators list. And while we're here, we might as well set up the object deactivators. So what do we wish to deactivate when this object is activated? And I think the only thing at the moment, based on what our scene currently contains, is just the light off game object. Remember, the light off game object is this red light, right? So we want to turn that one off and then activate light on. Let me put light off back on again. And then selecting our switch trigger, let's drag light off into that slot in the object deactivators list. All right, so when we activate this switch, we're going to enable the light on game object, that's the green one. We're going to enable the public announcement, the engine sound, and all of those lights, and we're going to turn off this red light here. Okay, are we ready to see what happens here and whether this works? Hope for the best. Okay, here we go. Let's hope everything works. Hey. There's our running engine sound and the public announcement.
Attention all personnel. This is an automated message being broadcast on the Simtech Emergency Broadcast Channel. Quarantine Zone ACE.
And you can see all of our lights have come on over here as well now.
Affected personnel should implement.
And let's just check that the power state has been set to true. Yeah. Okay, well, that was a bad test actually, because I think at the moment I've set all the states so I can use the keypad. So we better just do one more test there by selecting our application manager. Yeah, you can see by default I've set power to true, lockdown to false, and access code to true. So let's set all of those things back now. Let's set access code to false, and let's set power to false as well. And we'll set lockdown to true. Okay, so when I press play now, we can't use the elevator. It says no power. But if I go over to the power generator, activate it, and then go back to the elevator, you can see that it no longer says that we have no power. That's because our generator correctly restored the power state. So now it's telling me that we're under lockdown, and that's why we can't use the keypad. Okay, so I'm going to leave it there for this lesson with a fully functioning power generator. Like I said, the only thing it's not doing at the moment is turning on the computer system, but once we've created that computer system hierarchy, it's going to be really simple just to select our switch trigger, add one more element to the object activators array, and then just drop a reference to it in there, and then the power generator will automatically turn on the computer system. So we now have a really powerful generic trigger switch which we can use in the further development of Dead Earth. And we also have this really interesting material controller class which allows us to apply changes to materials and also safely so that they restore themselves when we exit the scene or the application. So thanks for listening, folks. I'll see you in the next video. Goodbye now.